So now we're going to apply using the determinant to find missing entry values inside the matrix. So you'll notice in this example, it's asking us to find x. So just so that we can kind of see where x is located in 2 entries of this 3x3 matrix. We also notice that it's actually given us an equation. We see this equal to 0. And even understanding what this means, you do see the bars. So that is full on letting us know that we have to actually compute the determinant so that we can solve this particular equation. So one thing I want to notice for you or call to your attention is that since you have variables as entries in the matrix, you can't just plug this determinant into your calculator. So we will have to do the expansion by minors so that we can calculate this determinant by hand. So let's do that. If I'm going through this, the first thing I'm going to understand is if I am using expansion by minors, I am going to look at the array of signs or the corresponding array of signs. And what that gives me is the same dimensions, a 3x3 determinant, or 3x3 matrix. And top left corner is plus, and everything alternates from there. So from here, I'm going to choose a row or column in this particular original matrix to expand out by. And I don't see any rows or columns that have zeros, so I'm just going to go with the first row. And if I use the first row, we're going to write out the entries. So 1, -3, and -4. And alongside with the entries, I'm going to pick the corresponding row in the array of signs, and I will be multiplying the signs by these entries. So we have plus positive times positive. Here we'll have negative times negative and positive times negative. Now, after I have that accounted for, the next thing I'm going to do is figure out the minors for each of these entries. So again, with doing this, we're going to cover up the row and column that the particular entry is in. So right now, when I say cover up, I'm using the highlighter. So we'll just kind of think about the entries that are not highlighted are the leftovers. So the row is already covered up. So if I am looking at where the 1 is located, I am going to cover up the column it's located in. And if I do that, I have my leftover entries. So I'll write them in order: 4, x, 3, and 1. I'll do the same thing for the -3. So again, I have the row covered up. Now the column that I want to look at will be covered up as well. And I will have remaining entries in the matrix. So I may need to space this out a little bit, but I do have the 3, the x plus 1, the x, and the 1. Now, one last entry to account for, covering up the row and column that the -4 is located in. And we'll have the resulting entries for this minor as well. So I'm going to have a 3, 4, an x plus 1, and another 3. So now we've taken care of expanding by the minors. Now it's just a matter of calculating the determinants and simplifying the expression. Keep in mind though, as we have expanded by the minors, the goal is not just to calculate the determinant. The goal is to solve when the equation is equal to 0. So I'll continue writing equal to 0 to help us with that. So starting off, I'll just simplify the number in front. This is positive times positive, so we still have a 1. I will then calculate the determinant of this 2 by 2 minor. So again, we're saying 4 times 1. We'll subtract off 3 times x. The next one, I'm looking at multiplying the signs. Negative times negative is positive, so we should have a +3 as a factor. When I do calculate the minor, or the determinant of the minor, we're going to, again, multiply the diagonals. So we have 3 times 1, and subtract off x plus 1. Let's spread this out just a little bit. So x plus 1 times x. And we'll have to kind of think about that in a second, just to make sure that we're simplifying it correctly. So same story with the -4. We have positive times negative, which will give us a -4. We then calculate the determinant of this 2 by 2 matrix. So we have 3 times 3 and x plus 1 times 4. And reminding, let me write it a little bit more over, reminding ourselves that we're subtracting the products. So keep that in mind. We still have this expression equal to 0. Reminding ourselves we're solving an equation. So now we'll take the time to simplify. We have 1, I'll keep that intact. 4 times 1 is 4. We're subtracting off 3 times x, so we'll just write 3x. We have +3. And then if I'm saying 3 times 1, then we have 3. And then just so that we're understanding this, it could be useful. We do see that we have a binomial times a monomial. If it helps, we can reverse the direction of the multiplication. A lot of us rather see the monomial first. So I'll do that. And if I am simplifying, I have to remember that I'll be distributing the -x to both terms. So I will have -x times x, which would be -x squared, and -x times 1, which will be -1x, or just -x. So that's the value of that determinant. And I'll do the same thing with the 4. Again, if we notice, we have 3 times 3, which is 9. That's fine. And then again, we have a binomial times a monomial, x plus 1 times 4. So if it helps you, and I like to rearrange things for myself as well, I'll kind of rewrite it. So I really have a 4 times x plus 1. All I'm doing is reversing the order in which I multiply. And then if I'm simplifying this, I am distributing a -4. So -4 times x is -4x. And -4 times 1 is -4. So we still have everything equal to 0. Let's keep that in mind. Now I just kind of go through and I can start simplifying. I see that I have a 1 times 4 minus 3x. I know anytime I multiply something by 1, it is true that you are distributing, but we still end up getting the same thing, 4 minus 3x. I do have a 3 that I can distribute. So 3 times 3 is 9. 3 times -x squared is -3x squared. And 3 times -x is -3x. And then perhaps, I mean, I can do distribution too, but I may look at this -4 part, and I know that 9 minus 4 is 5, so that might be quicker for me to deal with first. I've got those like terms. So I have 5 minus 4x. And it's just an extra step. If you can mentally distribute, or if you feel that it's unnecessary, then just be really careful. I'm really big on writing out my steps in these types of processes because it is so easy to lose a negative sign here or there, and then you get really confused as to where did I go wrong. So just take your time and be patient. We have a lot of paper or room for that, so I like that. So at this point, I'll just write everything out that I haven't used. I'm just recopying everything over, but I'm reminding myself that I am distributing the -4 times 5, which is -20. See if that'll write out for me. There we go. And -4 times -4x is positive 16x. So we still have all of this equal to 0. And now we've gotten rid of the parentheses by using the distributive property. So now it's time to combine like terms, make our lives slightly easier. So I'll just scan through everything. And the first term I see on the left-hand side of the equation, I do see a 4, that's a constant. So I do see a 9 as a constant and a -20 as a constant. So I'll just combine those. So I have 4 plus 9 minus 20. So that's giving me -7. Now I look at my linear terms. I do have -3x, another -3x, and a plus 16x. So that's going to leave me with plus 10x. Let's write that a little nicer. And then I do have one quadratic term. That is just -3x squared. I'll just write that over again, and just kind of keep in mind we still are equal to 0. Now, notice if you're going to now solve this equation, we do see that the highest power of x is 2. So we do have, in fact, a quadratic equation. So we have to go through all the techniques on how we would solve this quadratic equation. First thing I like to try is see if I can factor it. It looks like these coefficients are a lot smaller. They're not huge numbers or decimals. And maybe just to get the gears in my mind moving, I might rearrange in descending order. So I might write the -3x squared term first, positive 10x second, -7 last. There's that descending order. I'll set that equal to 0 because it still is equal to 0. And then, you know, if I'm trying to factor, I always get annoyed, and that's my personal problem, I'm sorry. When I see a negative in front of the x squared, I like to avoid that. So what I'll be doing is I could factor out a -1, or basically I just move everyone over to the other side. So it's kind of the same idea. So I'll just kind of show you what factoring out a -1 does. It's kind of like adding the opposite so that it's moving to the right-hand side. But I'll try to stay consistent with keeping everything on the left. So if I do factor out a -1, you'll notice that I get a positive 3x squared, a minus 10x, and a positive 7. All it does is change the signs. And then what happens with this -1, technically it's a constant multiplied by an expression. So what you can do for yourself, make life easier, basically divide it out. So if you divide by -1 on both sides, you end up getting a 1, and 0 over -1 is still 0. So really what we're left over with is 3x squared minus 10x plus 7. So now we have that nice positive square term, and that helps us just kind of with the factoring a little bit better. I'm going to try using the A times C method. So I have factors of A times C, so that's 3 times 7, which is 21. That add up to my B, which is -10. And so let's see, if we're looking at factors of 21, I have 1 and 21, that's not gonna work. The other one's 3 and 7. And if I have to make a positive 21 and a negative 10, I'll then have to choose both of them to be negative factors. So we do know that it factors. What we want to be careful about is that our leading coefficient, or the coefficient of the x squared term, is not equal to 1. So our a is not equal to 1, it's actually equal to 3. So when we choose our factors, which would be, what do we have, negative 3 and 7. Negative 7. What we would have to do is we have to divide by a. So we're going to divide both sides, well, not really both sides, but both factors by a equals 3. And this, my friends, is the bottoms up method if you haven't recognized it. There's other ways to factor. Feel free to use what you like, but this is just my favorite way. So I have negative 3 divided by 3. So if I reduce that out, I should have a negative 1 over 1. And then negative 7 over 3, nothing really happens. Now if we use bottoms up will say that the denominator is the coefficient of the x in the binomial. So we have 1x minus 1. The numerator is the constant. Again, 3x minus 7. There's the bottoms up. So this particular factorization, we will say, I don't have to put the 1 in front of the x. I'll have x minus 1 and 3x minus 7. And remember, we're still equal to 0. So we are almost there. We just need to solve for x. So what we have to do is we just set each factor equal to 0. I'm sure you've done this many times now by the time we're over here. So I have x minus 1 equals 0. Our 3x minus 7 equals 0. And so we do get a value for x. X could equal 1. Or let's see if we move the 7 over. 3x equals 7. Divide both sides by 3. X could equal 7/3. So pretty much, well, you could either circle both of them. There's two possibilities for the entries in this matrix. That's interesting. So final answer, you can either circle the x's, or if you'd like, you could just write them in set notation, where you have a 1 and a 7/3. And so that's quite an algebraic process. What I like about this problem is it really unites some of the new concepts of finding determinants using that expansion by minors. And then it kind of brings you back to the basics of, we got to solve this quadratic equation. And how do we solve quadratic equations? Well, we can try to factor. And if it factors nicely, good. But if we're not comfortable with factoring, or we're just having a hard time finding those factors, you probably would resort to using the quadratic formula. So we do have our solutions. We're in good shape. I hope this helps you for these examples in the homework. I'll see you in the next example.